All right, everyone, our homework last night was worksheet number 3. It was on work, and we had questions 4 through 8. Any issues with any of those questions 4 through 8 that we should go over here? Number 7, 8, 7, and 8. Okay, so both of those questions that we didn't look at yesterday at all. All right, 7 says a 2.00 kilogram box slides down a 1.5 meter high hill at a constant speed of 4 meters per second. Let's draw it out here, okay? The hill has a height of 1.50 meters. The 2 kilogram box is sliding down the 1.5 meter high hill at a constant speed of 4.00 meters per second. The distance covered by the box is 4.60 meters. So this is 4.60 from top to bottom of the hill. We want to know what's the net force acting on the box? Okay, take a step back from this one for a second. This is an easy question. What's the net force acting on the box? What's the net force acting on any object that's moving at a constant speed? Somebody this morning came in for a little bit of help on this. Okay, and I gave them kind of a way to think of this, and then they showed me what they did. I can't remember who it was. They showed me what they did. Basically said, does this work? F is equal to m times a. If it's going at a constant speed, where a is equal to 0 because it's a constant speed, then the mass of 2 times 0 is 0. Does that work? Sure it does. The net force is m times a. The acceleration is 0. The net force is 0. You could do it mathematically like that, absolutely. But you could just look at it and say, look, I know that any time it's traveling at a constant speed, the net force has got to be 0. Doesn't mean there's no forces. It just means they balance so that the net force is 0. So do it mathematically. Do it kind of conceptually like I do. I don't really care because they're both correct answers. Now the next part of that question says, how much work does friction do on the box as it slides down the hill? How much work does friction do on the box as it slides down the hill? Well, if it's moving down the hill, there is a force of the hill acting down. There's got to be friction opposing it. Otherwise, it's not going to move at a constant speed. How much work does that friction do? How much energy does that friction take away from this box? Well, we know that work is equal to F times D, but we also know that it's equal to delta E. That's the work energy theorem. Okay, remember that. Okay, remember that. You can do W is equal to F times D. You can do W is equal to delta E. Both are legitimate. In this case, we're going to say W is equal to delta E. It's the final minus the initial. Now, what kind of energy does this box have when it's reached the bottom of the hill? Does it have a height? Yeah. Oh, yeah, go ahead. Well, after it reached the bottom of the hill, it would stop. But as it gets to the bottom of the hill, it doesn't have potential anymore, right? Because it's got no height. But it does have kinetic, right? It's moving. But the kinetic's not changing. So since we're looking at the change in energy, let's not pay any attention to the kinetic because it's not changing. The kinetic exists at the beginning and the end of the question, and it's both the same amount. So don't worry about it. It's not changing. Don't worry about it. If we're ignoring the kinetic, then we're going to say the final energy is 0 because there would be no potential. The initial energy would be what if we're ignoring the kinetic because it's not changing? What kind of energy does it have at the beginning of the problem? Janessa, what kind is it at the beginning? Yeah, it's gravitational potential. So 0, the final energy, minus the initial energy, mgh initial. Let's figure out what that is. 0 minus the mass of 2 times 9.81 times the height of 1.5 meters gives me negative 29.43 joules or negative 29.4 joules. Why is it negative? Because it's down? No. Why is it negative? Because it was a loss of 29.4 joules of potential energy. Well, what caused that loss of potential energy? Friction. How much work did friction do? Neg 29.4 joules. That's how much work friction did. Now, we want to find the force of friction. We got 2 equations for work, right? We just used one of them. Which one are we going to use now? Kathleen, what do you want to do now? We got the W. We want to find F. Good. Work is equal to force times distance. This time it's going to be the force of friction. If we're using the work, the change in energy caused by friction, then the force that we solve for there is going to be the force of friction. W over D, the work done by friction, negative 29.43 joules, divided by the distance, 4.6 or 1.5? Which one do we use? Which one do you use? 4.6, right? Because it's the distance over which the 2 kilogram object moves, the displacement of the object. So we're going to say 4.60. We do that math, it works out to be, F works out to be negative 6.40 newtons. Now, the negative in the work's a scalar. The negative doesn't mean direction. It means a loss of energy. Force is a vector. The negative means something in terms of direction. What does it mean? Backwards, right? If the object is moving down the hill and we make that positive, then the force has got to be negative, the other way around. Yep, Kate? So gravity doesn't have a negative on it? Good question. Why doesn't G have a negative on it? Why don't we make it m times neg 9.81 times I? That's a good question. Does anybody want to suggest an answer before I give mine? Why doesn't G have a negative in front of it? Yeah. Okay, that's a good observation, actually. Negative 9.81, negative 1.5, because it's downwards as well, right? If it's a displacement. The only problem with that is h isn't a displacement, h is a height. So it's not even a vector, it's a scalar. Here's the thing. Potential energy and kinetic energy are both scalars. We don't want a direction with them. So when we're calculating that scalar quantity, let's just plug in the value of gravity, 9.81. Let's not worry about the direction because the energy itself doesn't have a direction. Does that make sense? So if you're finding the force of gravity, you got to use neg 9.81. If you're finding the gravitational potential energy, you don't use neg 9.81, just use 9.81. Force is a vector, potential energy is a scalar. Is that question okay? Mathematically, it's a cinch here, right? It's just a matter of getting to that point where we get to do the easy math. All right, number 8 says an elastic. Oh, we haven't done any of these work problems with elastics, but that's okay. Our thought process is no different than it is for any other question. Number 8 says an elastic with an elastic constant of 20 newtons per meter is stretched 4.50 centimeters. What's the average force that must be applied to the elastic to stretch it this far? We're saying average force here because the reality is as you stretch it further and further and further, the force changes, right? We know that by Hooke's law back in our last section of the unit. F is equal to kx. X gets bigger, F gets bigger. We're looking for the average force here. We get a spring constant here of 20 newtons per meter. We have a displacement here of 4.5 centimeters or 0.0450 meters, and we want to find the force. Now, if you use F is equal to K times X, which I know that some of you did, you're going to get 20 times 0.045. What does that give me? 0.090 newtons, right? But that's not right. Because that force is not the average force, right? That force is not the average force. Make sense? The force is changing. That's the force that exists when the displacement is this value. What's the average force from when I pulled it from nothing to that value of displacement? Well, let's use energy for this. Let's try a work analysis here. Let's say W is equal to delta E, the change in energy. The final energy is potential, but it's not 1/2, it's not mgh potential, it's 1/2 kx squared potential. That's the final energy. As you stretch a spring, it has potential energy after you've stretched it. What's the initial energy? Before you stretch that spring, the spring has 0. So it's 1/2 kx squared minus 0. The work here works out to be, oh, sorry, I gave you an answer in number 8 that's wrong. I gave you the answer for work. 2.03 times 10 to the negative 2 joules. Well, that's the work. Let's find the force now. If it's stretched 0.045 meters, then the object on the end of the elastic has moved that far as well. The displacement of that object is 0.0450 meters. We solve that. What do we end up getting there? Not sure what the answer is because I didn't finish that on my answer key. I get 0.451 newtons. Anybody get that? Good. How many people got 0.9 newtons using F is equal to Kx? Right, when we use that, F is equal to Kx, we get 0.9 newtons. 0.045, sorry, K is 20, times 0.045 works out to be 0.9. It's twice the value of this, right? We said that this one was wrong. Why? Because that's not the average force that we've just found. What we found there is the maximum force. When you've stretched at a certain distance, that's the force that's being applied when it's at full stretch. That's the maximum force. What's the average force going to be? Well, if the initial force is 0 because it's not stretched at all, and the maximum force is 0.9, then the average force will be half of that, 0.45. And lo and behold, that's what we end up getting, right? So you could do it this way, but you got to recognize when you solve for that force, it's not the average force. It's the maximum force. You'd have to divide that by 2 to get the average force. Okay, I think that's a little bit tricky. Okay, even though mathematically it's easy, I think conceptually that's a little bit tricky. Okay, I think this is a little bit harder mathematically, but a little bit easier conceptually to recognize that, look, solve for the force, that's the force we want. We don't have to divide it by 2 or multiply it by 2 or anything like that. Is that okay? Good? Question? No? Okay, we're going to have ourselves a little quiz on energy and work. Energy and work tomorrow. So, quiz on Wednesday. Talked about power a little bit yesterday. That won't be on the quiz. We'll talk about power a lot more today. It won't be on the quiz, okay? Just this stuff on energy and work. Right? No crazy hard questions. Probably not anything quite as hard as number 7. Okay, if you're okay with the rest of the questions, you're probably in pretty good shape for this quiz. Right? Yesterday we defined power as the rate at which work is done. How quickly work is done. Power relates to work. But it's not just related to work, it's related to the time. So when we talk about power, we're not quantifying how much energy you've expended. We're not quantifying how much energy you used up. We're quantifying the rate at which you used it up. You could do very little work. You could do just a tiniest little bit of energy expenditure, but your power output could be very, very high if you did it quickly. Yesterday, we did a little activity where you ran up the stairs and we found the power output of your legs. The power output of your legs ranged anywhere from about 300 watts to about 1,200 watts, depending upon the person. 1 horsepower is defined as about 746 watts. That means if you had a power output of 1,000 watts, you had about 1.5 horsepower. You were as strong as about 1.5 horses. That's good. But you only did it for about 3 seconds. So you expended a lot of energy in a very, very short period of time, meaning your power output was high. But it doesn't mean you did a whole lot of work. If you had to do a whole lot of work, then your power output would probably go down quite dramatically because you probably couldn't sustain that power output. But listen, for that 3 seconds that you were running up those stairs, you can take this to the grave in 80 years when it's time. For those 3 seconds, you're stronger than a horse. You're more powerful than a horse. Some of you, that is. Some of you are only half as strong as a horse. Okay? So it's the rate at which work is done. It's how quickly we do work, not how much work we do. All right. So we identified an equation yesterday that kind of relates to the definition. Power is equal to work over time. Well, we know that work is delta E over T, so we could also write the power equation like this. Delta E over T. Work is delta E. Power is equal to work over time. Power is equal to delta E, the change in energy over time. What are the units, by the way, for time? I mean, that's day one, right? Day one of physics 20. What is it, Dustin? Seconds. Good. What are the units for work or for delta E? We just learned that a few days ago. Better know this. Right? Joules. Good. So what are the units for W over T or delta E over T, Ryan? Yeah, we can say watts. Yeah, absolutely. Capital W or joules per second. Good. A watt is equal to a joule per second. I don't care which one you use. Okay? I'll sometimes use joules per second. I'll sometimes use watts. It means exactly the same thing. Okay? The rate at which work is done is the joules per second, not the joules, but the joules per second. All right. So you did your little activity yesterday, and that served as a little bit of an example. That was a little bit of an example for us. Let's do one more example. Okay? We'll use somebody's data from yesterday to find their power output. Okay? Instead of doing an example from a book, that will be our example. Okay, let's use Dustin, I think, had the highest power output, right? So let's use, well, the second time that is, he had the highest power output. The first time, I think he fell on step number 2. So it didn't work out. You got to redo a mulligan. That's why he golfs so well, is because he takes mulligans whenever he has a bad shot, right? Dustin, what's your mass? So Dustin's mass is 79.0 kilograms, we'll say. The height of the stairs were 3 meters. 3.0 meters. And Dustin, what was your time going up the stairs the second time when you actually made it all the way up? T was 1.72 seconds. The first time was infinite because, of course, Dustin didn't make it all the way up the stairs. I'm sorry? Yeah, but did you run up the stairs or did you walk? See, yeah, he's pretty good at going up the stairs when he's walking, right? Plus, you weren't thinking. It's hard to walk and think at the same time, isn't it, Dustin? We want to find the power output. So we know that power is equal to work over time. Now, we also know that work is equal to F times D. And we also know that work is equal to delta E. Let's use the delta E part of it here. Okay, delta E over T. You could say F times D over T if we knew what F and D were, but we don't. Delta E over T, we do know what delta E is. The final energy of Dustin as he reached the top of the stairs was potential, mgh. The initial energy of Dustin before he started running, the second time when he made it all the way up the stairs, or the first time when he fell on stair number 2, I think it was. Is it stair number 2, Dustin? He did, by the way, make it for everyone here. He did make it all the way up the stairs today in the social class without falling. MGH final minus what? What kind of energy did Dustin have before he started going up the stairs? Nothing. He wasn't moving. He was standing there thinking about how he was going to get up the stairs so quickly. He didn't have potential because he didn't have a height. Potential energy was 0. His time was his time. 79.0 kilograms times 9.81. Who was it that asked me why 9.81 is positive? Okay. Again, we're talking about a potential energy which is a scalar, so let's just make it positive so that we get a positive number for potential energy. Final height is 3.0 meters minus 0 over the time of 1.72 seconds. Hey, don't calculate this yet. If Dustin's time was twice as much, let's say he made it all the way up the stairs, but he made it up the stairs in a time of about 3.4 seconds instead of 1.7 seconds. Would his power be more or less? Less. You get a number on the bottom that's bigger, his power is going to be smaller. What if he weighed more? What if instead of 79 kilograms, he was 85 kilograms? He's heavier. Would his power output be more or less? More. Why? He didn't do it any quicker. Because he had to do more work. If he's heavier, he has to do more work against gravity to get himself up to that height. The big people tend to win these competitions, right? The heavier people tend to win these competitions. Why? Because they're used to it. Their legs are going to be more powerful. They don't have to be quicker. They just have to be more powerful. And their legs are going to be more powerful because they're probably stronger. Hey, Dustin's legs are used to carrying around 79 kilograms. And a golf bag. And a bunch of extra golf balls for when he loses them in the water, right? Okay. I'm not sure what Luis's mass is, but it's not 79 kilograms. Okay. Luis's legs probably aren't quite as strong because he doesn't have to carry around 79 kilograms. Okay. His legs are as strong as they have to be to carry around whatever he needs to carry around. What do we get for the answer there? Dustin, what was that? Okay, 1,351.726, and the units would be watts or joules per second. We're going to round that to, we've got 3 digits here, right? 1, 2, 3, 2 digits, 3 digits. Final answer should be 1.35 times 10 to the 2 times 10 to the 3 watts. So Dustin was almost as strong as 2 horses over that short time of 1.72 seconds. No, you're right. Yeah, no, you're absolutely right. John makes an excellent point. It should be 2 significant figures. Because if we're going 3, 3, and 2, we always go to the least precise piece of data, right? So it should be absolutely 2 digits, 1.4 times 10 to the 3 watts. Thank you, John. That's why John sits in the front, so that when I make a mistake, someone's there to correct me. Okay. Is that good? It's not that hard, is it? Listen, sometimes you're going to get a question that's as simple as, here's the work, here's the time, solve for power. Those are easy. Sometimes you're going to get a question that's a little bit harder, like this, where you don't have the work. You got to find it. Get the work. Okay, we just did a whole worksheet on work. Get the work. Well, once you have the work, it's easy because you just divide it by time then. All right? I'm going to ask you right now to have a look at the 3 questions on page 325. Don't worry about solving for the power and horsepowers here. Okay, they give us the answer in kilowatts, joules, seconds. Okay, they've also converted it to horsepowers in minutes. Don't worry about that. Okay, just go with the standard units there. It's good. See what you do over the next 5-10 minutes, and then we'll take a look at those if we need to. Okay. Let's take a look at number 3, everyone. It says a tractor pulling a plow exerts a pulling force of 7,500 newtons over a distance of 3.2 kilometers. The tractor's power output is 25 kilowatts. How long does it take to do the work? Here's my force in number 3. And we've got a displacement here of 3.2 kilometers or 3,200 meters. The power here is 25 kilowatts or 25,000 watts. We want to find time. Now, I had a couple of people asking me questions like how do I figure out which equation to use and so on? Listen, if you're dealing with a question involving power, let's start off with P is equal to W over T. You don't really have to decide. If you're dealing with power, start off with that equation. Now, this time we have the power. Okay, we've got the 25,000 watts, and we're looking for the time. Our real problem here is that we don't know what work is. Now, there's a couple ways of finding work. Work can be found by saying delta E, and work can also be found by saying F times delta D. Which one seems to fit? Usually, if you're using the second one, F times D, it's obvious that you're going to do that. Okay, if you're not sure which one to try, number 1 or 2 work equation, then go with number 1. If you're not sure which one, go with number 1. Because usually if it's the second one that you should use, it's going to be fairly obvious that that's the one you're going to use. Which one should I use here? First one or the second one? Delta E or F times D? Let's see, if you've got a force and you've got a displacement, then let's use F times D. So let's say my power, my 25,000 watt power, is equal to F times D over T, or 25,000 watts is equal to 7,500 newtons times 3,200 meters divided by T. If you want to, find work and then plug the number into there instead of the expression. It doesn't matter. That means T goes up to the top, 25,000 goes down to the bottom. We do the math there, and I think it works out to be 960 seconds. Is that right? How many people got that one? It's kind of a tricky question, right? It's a little bit of a tricky question because it's not just work and it's not just power. It's both work and power. All right, if you're not quite finished those, then I'd like you to finish them. If you are finished those, I'd like you to take a look at worksheet number 4 in your energy worksheet booklet. And do all of those questions. Do all of those questions 1 through 7. There's a couple of questions at the end that are pretty tricky, okay, that are pretty challenging. Okay, try real hard to get the first 4 or 5 questions, okay, because they're questions that we need to be able to do for quizzes and tests. Last couple of questions, maybe a little bit harder than average, maybe a little bit harder than we even have to do. But they're good questions to go through so that it makes the other ones look a little bit easier, okay? Do your best on all of them. We'll probably give you the rest of class here to do these. If you do happen to finish them up in class, then we'll take a look at 1 or 2 of them today. If not, then we'll just take a look at them tomorrow, okay?